So the second speaker is Professor Michel de Waard from University of Nantes, France. Mesdames et messieurs, Michel is an expert in ion channel pharmacology and peptide toxin research. And he is also a founder of SmartOx Biotechnology, which is focusing on
peptide synthesis and toxin synthesis, yeah.
Yeah, I could not say it better. Michel is going to tell us about his work on photosensitive natural peptides to optically control ion channels.
Okay. Thank you very much, Artem, for the introduction. Thank you, Niels and Alison, for the invitation as well. Thank you for inviting a sick person as well. But no, I would just want to testify about the quality of the interactions we had with Nanion over the 8 years that we purchased the SyncroPatch. And we really had a high quality interactions and really helped developing the programs. So I'm going to talk about photosensitive peptides, and the principle of photopharmacology is to modify the drug's activity under the spot of a light, okay, and to give it some kind of spatial selectivity. In contrast to optogenetics, we are dealing with diffusible compounds. They are not attached to the cells themselves, and which is pretty important. So the advantages of photopharmacology compared to optogenetics is that you don't need any genetic modification of the organism, which allows it to go to the clinical applications more easily than optogenetics. The applications are not just limited to the control of cell excitability, of course, and it has a lower dependence to the depth of penetration of the wavelengths in the tissue because of the diffusible nature of the compounds. In contrast, however, it has a slower kinetic response and a lower spatial resolution. Now, why choosing natural peptides to do photopharmacology? Well, because nature has done the job, and there are millions of peptides out there that are tailored for in vivo use. The problem is mostly matchmaking the peptides with the targets. But it happens to be that most of those peptides are active on ion channels and on GPCR, which are two of the major classes of targets that are of interest for the pharmaceutical companies. Those peptides come into a variety of structures and secondary structures, but the main feature and the commonality of those peptides is that they are disulfide rich. And by being disulfide rich, they stabilize the secondary structures, and very often they make them protease resistant, and that's why they're so good in vivo. How this will compare later on to mini protein binders, and we're going to have an interesting talk after that, is interesting because how we can go with artificial intelligence to make new peptides will be of great interest. Now, we have developed 3 technologies, and I'll go over the 2 first one very rapidly, and then I insist more on photoactivation. So photoswitch is a reversible technology, okay? Photocoupling is, of course, an irreversible technology where the ligand gets coupled to the channel itself. And photoactivation is supposedly reversible, and I'll show you some data that eventually that contradict this idea. Here's Jérôme doing experiments. I want to thank Tom for the late pictures on the salt system that Nanion is developing, which is really going to be very useful for the projects. So for the first project, the photo switch, basically what we did is modify azobenzene in order to make it click chemistry compatible. And we use a model peptide that is really well known, caribdotoxin, which has been mutated on every single residue. And the docking is known on the Kv1.2 potassium channel. This is a pore blocker, and there's a lysine residue that's extremely important. The strategy here was to use to target some of the amino acids that are not involved in the pharmacophore of the caribdotoxin. Okay, so that should not hinder the binding of the peptide. But the idea by grafting azobenzene here, the tryptophan 14 has been modified by azidohomoadenine for the click chemistry. So we add the azobenzene, and the idea here is depending on the conformation of the photo switch, trans or cis, the hope is that the azobenzene is going to interfere with the pharmacophore, right? And this is exactly what we're seeing here. The cis conformation being the most active and the trans conformation being the least active. And what you see is that you can dynamically regulate the potency of the block of charidotoxin by light, and you can repeat this experiment several times. So I'm not satisfied by this, because this is a small shift, but all of those photo switches, including with the small compounds, are giving similar results. Irreversible property. So what we did here is take another model peptide with PAKM1, which is a peptide that binds onto the ERK channel, the potassium channel. And it is also a pore blocker, and you have this lysine 18 that is blocking here. In this particular experiment, what we did is choose two of the pharmacophore residues that are not that important, which is difficult, serine 19 and threonine 24, and we substituted them with either photoleucine for the serine or photomethionine for the threonine. And those residues happen to have a diazerine at the terminal end of the lateral chain. And for those people that don't know what diazerine is that if you activate it by UV, you lose nitrogen and you form carbon, which is highly reactive and wants to bind to anything that is around. And this is what we wanted to look at. So what happens? We first checked that upon the substitution, we still have theoretically interaction with the channel for binding to occur. We then first illuminated the peptides to see what happens to the pharmacophore, because we're changing. The nitrogen is going away, and we are changing the nature of the pharmacophore by doing so. And what we see, it's interesting, is that on serine 19, by photoactivating the photoleucine, we have a gain in potency of the peptide. Conversely, on the photomethionine, we have a loss in potency. Okay, so this is coherent with the change in the pharmacophore. We tried to understand what is going on with those modifications. We found out that a large part of the carbon is interacting with water in different ways, with the solvent, which is logic. And another part, actually, you have a restructuration of the photomethionine in this particular example, indicating that part of those interactions no longer can occur with the channel, and that's making it far more complicated. So what happens now if we do it dynamically in the presence of the channel? And what you see is that for the S19 photoleucine, if now we apply light and coherent with the gain in potency, by light we change the pharmacophore and we have a gain in potency of the peptide. For the threonine 24, we have a loss in potency that is also coherent with the change in the pharmacophore. But if you look well, over time, you regain potency, suggesting that you have interaction with the channel occurring. And this is exactly what we see here, although the Nanion system, unfortunately, not good enough for reversibility, but still, what we do see is if we wash out this peptide naturally goes off the ERK channel, with light at 365 nanometers, with this particular peptide, we see that we have very little reversibility and recovery from the block, suggesting that we have this interaction occurring. Okay. So we haven't done in vivo experiments yet, but we hope to shift to that later on. Now I'm going to talk about the third technology, which is photoactivation. Okay. And we take again this BAKM1 as a model peptide. And as I told you, or maybe not, but the lysine 18 is a very crucial residue in the pharmacophore of the peptide. Okay, if you mutate it, you lose most of the interaction. And what we did here is add a photosensitive protecting group, which is called NVOC. I'll make it simple. And what happens if you do that? You create steric hindrance for the binding of the BAKM1 in the pore of the channel. Now, not only do you create steric hindrance, but we did some NMR experiments, you also see chemical shifts in the amino acid residues that are surrounding the critical lysine 18. Okay, so we have two reasons to believe that we're going to lose the interaction of BAKM1 with the ERK channel. And this is exactly what you see here. You have a 3-log shift in the potency of the peptide. Meaning that at high concentration, non-active high concentration, we have this sweet spot here, where even 1% uncaging would be sufficient to block the channel. And that 1% is important. We did this also for uventoxin 4. For those people that don't know, uventoxin 4 is a peptide block that blocks voltage-sensitive sodium channels, except NAV 1.4. So here it's not lysine 18, it's a lysine 32 that is critical. And we have exactly the same story. We have steric hindrance for the binding on to voltage sensor domain 2 of the sodium channels. It's a gating modifier this time. And we also modify the surrounding structure of this lysine 32. And sure enough, on all NAV NAV channels tested, we have this 3-log shift in the potency of the peptides upon adding this photosensitive group. Okay, now we also made a number of other peptides to make it a generic method for regulating NAV 1.4, NAV 1.2. This is an activator. It's producing a late current. It's looking for those people that know about ATX2. It's producing a late current on the sodium TTX sensitive channels, on the anti-calcium channels, and on the KV 1.2 as well. We checked that uncaging can be complete with light. We also checked the kinetics of the uncaging, but it takes about 10 minutes to completely uncage at maximal power. But as I told you, we need just 1% of uncaging to get a beneficial effect. The power dependence has been treated, and the wavelength dependence, we can go up to 405 nanometers to uncage. Okay, it's not UV. In vitro, it works. If you add cage BAKM1 on HEK cells expressing the ERG potassium channel, we have no effect. If we add light, then we see the appearance of block. On cardiomyocytes derived from human iPS, and with our action potentials, you see that we encage the peptide, we prolong the action potential durations, which is coherent with the role of the ERG channel in the repolarization of the cardiac action potential. And we also trigger early after depolarizations, which is the first sign of arrhythmia, which is coherent with the role of the ERG channel. We also succeeded this on NAV 1.6 expressing in HEK cells. You also see that you have no effect of the peptide. Light is producing the block of NAV 1.6. Here we checked a little bit of the spatial resolution of the technology. So basically what is done here are those brain slices where we record cortical neurons and we record the action potential in the soma of those neurons, okay? And we have this spotlight, which is 20 micrometer away from the cells, 20 micrometer in diameter, sorry, and we progressively approach it to the soma. And you can see that at 100 micrometer, we activate the peptide, but we have no effect on the action potential. The closer we get, the more we block. Okay, so we start having a resolution that's around 60 micrometer for this technology. Does it work ex vivo? Yes. This is a heart, red heart, sorry. They don't express really well ERG channels, okay, but they do to some extent. So what we did here is illuminate, and what we see is that uncaging the BAKM1 is producing a slight bradycardia of the heart, which is coherent for the role of this potassium channel in these animals. We also produce conduction defects. This can be repeated on a rat with that undergoing mini thoracotomy and the anesthesia. And what we are doing now, we no longer apply the peptide to the heart itself, but we inject it IV. This is a cage compound. It no longer recognizes the potassium channel, but still it goes to the tissue and to the target, because when we illuminate the heart, we produce again bradycardia, okay, and that is important. And the next step here is is zebrafish, and on zebrafish we did the same experiment. What is producing? It's producing bradycardia upon photoactivation, sorry, and also atrioventricular block. Sometimes you have atrial contraction and no ventricular in the zebrafish. Okay, and this was probably the most difficult experiment that the reviewer asked us, is we took this caged UV toxin, and as I told you, it's active on TTX sensitive sodium channels, but it's not active on NAV 1.4. So at the neuromuscular junction, UV toxin is going to block NAV 1.6, but not NAV 1.4, okay? So here's the system. This is the mice, nest size. We take the EDL muscle. It's connected to a transducer, and we stimulate the nerve, okay? And the peptide, the cage peptide, is injected IP. Sorry. We then apply light. Without the peptide, we have no effect of light. But with light, we see, sorry about that, we see a progressive block of the contraction. Now, and to finish, this is what Matthias is doing, a PhD student with the Guthruff Lab collaboration. We're using a receiver and controller unit with that's controlled by radio frequency, and we have a stimulation pad that has lead. So this pad is stitched onto the heart, and this is put under the skin, and then the animal is freely moving for a month. And here's an experiment where we injected the caged AH2, which is producing a late current in the TTX sensitive sodium channels. Because there are TTX sensitive sodium channels in the heart. And upon light activation, we see that we have an elevation of the ST segment, which is coherent with a defect in repolarization. If we shut off the light, then we go back to normal because the peptide is circulating. So it's going to be active under the light spot. But if you stop the light spot, then it's going to be diffusing away again from the spot of the illumination spot. So I hope I convinced you that natural peptides are suitable molecular platforms to empower them with photosensitive characteristics. The three technologies are really differing in the way amino acid residues of the peptides are being used. The first one, we don't want to use residues from the pharmacophore. The second one, you want to use not so essential residues from the pharmacophore. And in the third one, you want to use the most important residues of the pharmacophore. And I think what is important, and this is where we try to work with, is to go to in vivo applications with those peptides to be competitive, I suppose. Okay, and I want to thank everybody here, of course, the Nanion team, and all the collaborators and the team members for helping with those projects. And thank you for your patience.
Merci beaucoup, Michel. C'était formidable présentation. I never get tired of listening your stories. It's very exciting. So, audience, do we have questions to Michel?
Very nice work. Thanks a lot. So one of the questions I had was, you mentioned that the deprotection, if you can call it that, is quite slow. Could you speed that up by using a different protecting group?
Yes,
like that?
yes, we are looking for that. Kinetics is the key here. I mean, you want, because, I mean, nobody knows about diffusion peptides in tissues, in fact. You know, this is a completely new world. So peptides are going to the tissue. How long do they stay? How fast do they diffuse away? So if you illuminate, you're in cage. And you don't have the time to reach a concentration for an effective effect, then it washes away, you know. Then, so therefore, you really need something. You really need something that engages fast. So we're looking for new cages, but it's already working this way.
How about the stability of these peptides when we inject them in bodies? Are they stable? No.
Yeah,
most of the time when we tested it, we say 10 hours. Because those are natural peptides. But of course, if you want to go to real applications, you have to prolong this a lot. But that technology is now out there for prolonging the half-lives of peptides.
Okay, thanks so much, Michel,
Thank you.
for this presentation. Yes.